So with that, I would like to introduce Jafar Abdul, who will be presenting software-defined backbone, experience with a deployed SD-WAN. Jafar is a senior staff and software engineer at LinkedIn and traveled from San Jose, California to join us today. This is Jafar's first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Jafar is joined by Prashant Kumar, who is working as a senior staff network engineer at LinkedIn, leading the design and execution of large-scale network initiatives across data center interconnect, backbone, and edge infrastructure. Welcome, Prashant and Jafar. The stage is yours.
This is forward. Backward. Or do you do back? Thank you, Michael. My name is Prashant. I work in Network Engineering Operations Group as a network engineer. And I'm here with Jafar from Network Engineering to present the challenges we faced in our backbone with the inter-DC demands. It's not cool. Okay. You guys may be wondering how big is LinkedIn Infra? We have 1 billion members in our platform. We operate multiple data centers. We have 500,000 plus servers in our environment. And we have 3,000 plus services running in our platform. What are the challenges we had in our backbone? We operated a classic RSVPT backbone with auto bandwidth for internet and inter-DC traffic. As you can see, we have this backbone connecting to transit and peering, where the eyeball traffic came in and get terminated to the edge pop. And from the edge pop, it went into the DC. And the same network is used for inter-DC traffic as well. Traffic between the data center use the same backbone. We ran into 2 issues quickly because the inter-DC traffic grew exponentially, while the internet traffic growth was linear. And inter-DC traffic was bursty because there are a lot of offline jobs get pushed into other DC and replication jobs get pushed to other DC. And these traffic were very bursty and it can eat up all bandwidth in the network. We also had issue with efficiency. We are not able to prioritize an ability to use all available capacity. What does it mean? Because the same backbone is used for different types of traffic. The inter-DC traffic, there are certain types of traffic which is optimized for latency and packet loss. That means traffic needs to go from the DC to DC with the shortest path and without any packet loss. But there are bursty traffic which can use all the bandwidth. But those traffic does not need to be the right away. There is an SLA by which that traffic needs to be on another data center. And this traffic can use all the available bandwidth. Right? So these are optimized for bandwidth. An operation standpoint, manageability overhead and RSVP lack global view. What I mean is RSVP is a distributed protocol. Depending on traffic burst, each of the head that computed the path independently, and there's probability that both the traffic end up in the same link, and it causes congestion. So we have to relook the external backbone. So what we did, we separated the inter-DC backbone and the internet backbone. So the internet backbone was dedicated for traffic from edge to POP and POP to DC, and inter-DC traffic was between the DC. We went with a planar architecture with ISI-SSR in the control plane and MPLS in the data plane. The planar architecture allowed us to scale horizontally. We can add more planes if you want to increase capacity. And we use ISIS SR in the control plane with source routing, which means it does not, none of the intermediate devices or tail routers need to keep the state of the path. The source decided what path to take, and it slaps onto the incoming packet, and the intermediate devices just switch based on the path. And we use MPLS in the control plane. And the scaling requirements of this backbone was very small. From the routing standpoint, we need few thousand routes, and we don't need any ACL, like the edge router, where we need to have a high ACL scale. So we could get away with the merchant silicon boxes, and we use pizza boxes for these routers. This reduced the cost drastically for this network. From the efficiency standpoint, we use centralized controller. This allowed us to have a centralized view of traffic demands and allocation with centralized prioritization. What it allowed us to do is to align our traffic based on business priority, right? So we are able to, we mark the traffic at the source. What I mean source at the host, centrally. And our network, there's a network trusts the marking, and controller steer the traffic through our network based on the priority, right? In either the shortest path or the longer path with more capacity. And the operational standpoint, we operate on network model on what, and we are global management really. What I mean is we define the intent, and the controller converted into config and pushed into our devices. And we could use the controller to do link drain if the link error, and node drain for upgrading or if there is an issue. And controller took care of rerouting the traffic to the other path where there's capacity. So this is shows high level the control plane design. On the left side, you can see the internet backbone, which has got yellow circles around it. And the right side, you can see the NGBB. And what the diagram shows two data centers, on the one on the top and on the bottom. And the circles in the green are the edge routers on the data centers. They steer the traffic to either, with the traffic going to the edge POP, goes to the BBR, and traffic going to the other DC goes to the NGBB domain, to the routers depicted in the red circles here. So the DCX or the routers shown in the red are the edge devices, and the intermediate router showing XPR in the green are the intermediate routers, right? So the edge routers, the DCX steers the traffic to the right plane. Once it enters the plane, traffic ride in the same plane and goes to the egress device, egress DCX, which is shown in red, and goes to the remote DC. So the DCX here, how does DCX steer the traffic, right? DCX steer the traffic controller pushes the policy on the DCX to steer the traffic XPR. So DCX will have the whole path, end-to-end path, and forward it to the right plane. So the packets have all the MPLS header to take the path in that particular plane. How does it look on a router, right? So centralized. So this is centralized policy management. Central controller is much more about the centralized controller. Centralized controller analyzes the traffic demands periodically, and when topology changes, and it computes the paths to satisfy the demands based on the priority. It pushes the policy-based router onto the ingress router, which was shown in the previous diagram as red circles, with class-based forwarding into weighted cost multipass. These are nothing but policy-based route applied to the ingress interfaces on the ingress routers. It's nothing but an ACL with source destination and DSCP value with next hop pointing to next hop groups, which is nothing but next hops with different weights. So basically, I'll show you a little bit more in the next diagram. So bear with me this slide. So the bottom diagram, it shows simplified drawing. So The numbers shown here are segment ID in SR routing. So basically, it represents a unique segment ID, and MPLS use this unique segment ID to create unique labels for each of those routers, right? So the traffic coming in on 201, this is like showing a policy-based route or an ingress router of 201 going to DC2, and it can exit either 205 or 208 on DC2 side. There's two policies there. So first one is DSCP 18, that is a low priority traffic, and DSCP 0, the second one, is a high priority traffic. And it's point to the two next stop groups. One is ending in 210-0 and 210x12. 210x0 was satisfied with the shortest path, that is 201, 192, 194, 205, and 201, 193, 195, 208. But the DSCP 18 is sending it could not be satisfied with the direct path, so it has to use it needs to use indirect path to satisfy the demand. So let's look at the next stop group 210x2 in more detail. So here you can see the next stop groups for the 2x0, which shows the labels. It shows all 4 paths. And the first path has got weight of 7, second path has a weight of 7, and the third path weight 1, and fourth weight 1. So the first two are ECMP path with weight 7 each. So the first path goes from 201 to 192 to 194 to 205 with a weight of 7. There will be 7 ECMP paths there. And the second path goes from 201, 193, 195 to 208. Again, the weight of 7. I mean, you don't see the 192 there because the traffic is forwarded to the next stop 10x13 and 10x14, which is the next stop. So that's why you don't see the label 192 in that path. But there are 15% traffic. I mean, there is some more traffic needs to be satisfied in the longer path. You can see like the next two paths are going to the 202, the next stop saying 10x12, and the labels you can see, the one of the paths goes to 192, which is on the tour to the top, and then go to 113, 194, 205, and the next one goes to the bottom 202 to 193 to 114, 195, and 208. So this is how the next stop label gets programmed on the router by the controller. So QoS is an integral part of this whole design, right? So ability for the backbone to prioritize traffic based on business priority was critical. So what we did is we managed the networking on the host. So we marked the DSCP packet based on the workload priority. And the data center network trusts the DSCP. And controllers steers the traffic based on the priority. And network control, so the scheduling of the control is the network control traffic have a strict priority, and rest of the traffic are scheduled based on the priority. So for this example, real-time traffic is scheduled next, and next is the next less critical traffic is prior. And in the end, if there is bandwidth left, we schedule the bursty traffic. Even though we do a capacity planning, and many a time there will be traffic demand, unplanned traffic demands, which controller cannot meet. This can be it can happen if there is a failure, multiple failures, which takes down more capacity than expected. So we have QoS, per hop QoS on the links. So it actually matches, it almost matches the controller scheduling. So we have same thing, priority queue, schedule first, and there is multiple weighted fair queuing with different weights. Real-time has 10%, online has 80%, and you say offline has 10%. Offline is nothing but the bursty traffic. So if the online traffic doesn't use the 80% of traffic, the offline bursty traffic can use the traffic. So this prevents us from critical traffic getting choked because critical traffic not getting dropped because of unplanned events. Migration, we went with two-phase migration. So in the phase one, we built the backbone, the greenfield backbone, and we migrated these two DCs at a time. So initially we migrated the management network between the DC, and then we migrated to DC. Then we gradually migrated the rest of the sites. We did this by advertising these networks in the new network and increasing the med for those prefixes on the old backbone. So it prefers the greenfield new backbone, NGBB backbone. On phase 2, we introduced the SD-WAN controller. So we did the pilot between 2 non-production sites. Then we added small subset of networks. Those are network like single top of rack, including some bursty traffic and non-bursty traffic. Once we have the confidence for a while, then we rolled out T between 2 sites and gradually rolled across all the sites. What is the impact? So we are able to use 95% capacity and cost efficient. We were able to translate QoS and better application performance. It simplified the network operations, and we also had end-to-end traffic path visibility and network health. With that, I will hand over to Jafar to talk about the software piece, which runs the backbone.
Thank you, Prashant. Good afternoon, Nanag. I know it's late in the day and we all had a wonderful lunch. So if you see someone sleeping near you, do not disturb them. They are just dreaming about software-defined backbone. I'm here to talk through the software side of LinkedIn backbone. First, let me cover the software design and architecture. We built this entire software stack from ground up, fully in-house. We used Golang for most of our coding. Since we used Golang, we naturally inclined towards using gRPC for service-to-service communication. Although we use interfaces like REST, GNMI, and gRPC towards talking to network devices. We embraced microservices architecture and deployed more than 1 instances just for redundancy. We fully automated workflows and configurations as well. We maintained code and source of truth SOT made separately. This setup allows network engineers to roll out any incremental network changes smoothly without bothering about the code. Next, I wanted to show you some of the key components in our software stack. I know this is a busy diagram. Just follow the color coding. All the green boxes out here are the services that are responsible for making changes in the network devices. The purple boxes are the services that reads operational states from the network devices. The orange boxes doesn't interact with the network devices directly, but it processes and aggregate informations for the entire ecosystem to work smoothly. We will deep dive into some of these components in the further slides. In our software stack, the front-end center is our centralized controller, which is doing the traffic steering. As Prashant said, the centralized controller takes advantage of the holistic view of the network and takes care of the entire capacity. We also compute paths for every traffic demand and convert those policies into policy-based routes in the network devices. As Prashant mentioned, we handle different type of workload marked as different type of priority. Our controller fast enough to react and catch up with any traffic conditions and changes in the traffic. To run traffic steering, we need 2 primary inputs. The first one is traffic demand calculation. The second one is the operational topology. Let's talk about the software traffic demand calculation for a bit. We use SFlow on all of our NGBB edge devices. If you remember the NGBB architecture diagram, those red round boxes are the edge devices. We call them as DCX. We use SFlow protocol to export flow data from the routers. We use a little bit of aggressive sampling rate 1:1000 because we have hardware S-flow support in all of our devices. We have multiple collector that processes flow data and aggregates and arrange them in this kind of a matrix form. These matrices are site to site, also sorted based on priorities and based on ingress devices. If you take an example, site A to site B is 120 gig. That's how the matrix are visualized and used in traffic allocations. The next key input is operational topology. As Prashant said, we use ISIS with a single domain configuration in our backbone. We naturally subscribe via GNMI to this LSDB info. The device sends GNMI updates periodically or when the topology changes. Our operational topology service consumes this LSDB updates and converts into an operational network graph, which is then used in our path calculation. Now let's take a deep dive into the core algorithm. We run algorithm every 10 seconds and most of the time it takes less than 5 seconds to complete. That satisfies our use case. We use CSPF, the constraint being the bandwidth. And it computes path for every traffic demand as long as there is a capacity. When we mean path, a path is basically starting from an ingress device, which is a DCX edge device, to all the way to the destination side on the other edge device. Thus, the entire chain of devices and interfaces are known as one path in this context. Once the paths are computed, if there is a demand that has multiple ways to reach, we use weights to differentiate the ratio of the traffic among the paths. These weights later translated into WCMP configuration and installed on the devices. Once the paths are curated and processed, these paths are sent to a devices via gRPC interface. An agent that is running inside the network devices converts these device agnostic paths into a device specific flow data and install them into the forwarding plane. We talked a lot about traffic engineering. Let's shift gears and talk about configuration management for a bit. We manage the end-to-end configuration of all the devices in the backbone. We use CLI only for debugging and troubleshooting. We allow humans to express a high-level intent and abstract out all the device-specific configuration from the software side. We use config generations based on multiple source of truths, network models, secrets, and various other information such as port profiles, hardware SKU, and so on. The last important function of our software suite is the safety and manageability. As we know, controller is a centralized entity. That means it's also acting as a single point of failure. We designed our network and controller in a way that when there is a failure encountered in the controller, the network automatically fallbacks to the IGP shortest path. This allows us to make sure that there is a readily available shortest path for the traffic that is coming. We also designed things like big red button that allow us to disengage the controller when needed. Touch wood, so far we haven't used this in the production. We also built utilities like drain and risk assessment that allow network engineers to take any part of the network for a maintenance without affecting a critical capacity that is needed for traffic steering. While building, migrating, deploying, and managing, we learned so many key lessons. I would like to share some of them with you. When it comes to the traffic steering, being deterministic is very important. Having a random path selection and allocation is going to be a debugging nightmare. Also, restricting a human to a high-level intent and abstracting out all the configuration internals would simplify the operation a lot. This also creates a paradigm of intended set versus the operational set. Now we can seamlessly compute the drift between these two sets and detect any network anomaly quickly. And all of this software has to run all the time reliably. That requires a huge investment in testing, regression, and simulation. And this would really pay off big time when it comes to pushing the incremental changes. This combined with progressive and safe rollout and rapid rollback will make our code much simpler and safer to run. Although we design controller to take over 100% of our traffic, in reality, there is going to be a little bit of dark traffic due to burst and various other scenarios. Accounting for this burst and accommodating capacity for this dark traffic is non-trivial and requires lots of trial and error. Also, when it comes to building visibility map between the controller provisioned path against the actual traffic that is being used in the network is a key in terms of debugging and troubleshooting any traffic issues. Also, when you rely on a vendor-specific implementation, that could affect our multi-vendor ecosystem. So, leveraging standard interfaces and standard protocols often allow us to easily port the solution over to multiple vendors. Thank you for listening to us and enjoy your rest of the day.
Okay. My name is Raju from Cruzo. So you mentioned about the red button, right? Like you can shut the controller, right? Can it be selective? Like can you shut the controller functionality only for a particular traffic path or the destination?
Yes, we could select a particular segments of the network such as a device or a link or a site and then disengage the controller for those particular entities.
Okay, thank you.
Do we have any more questions from the audience or remote? Okay. If no more questions, then thank you to Jafar and Prashant for a great presentation.
Thank you.